Well, hello. My name is Rob Tavani. I'm going to be conducting the webinar today. My colleague, Atta Fabibula, had to be out of town today, so he asked me to conduct this webinar, and I'm very happy to do so. So today we're going to be talking about rigid and semi-rigid diaphragms. And I really believe that this is one of the things that you have to put on your checklist when you're creating an analytical model. You really have to ask yourself, how am I going to treat the floor diaphragms? And there are times when it's completely appropriate and desirable to treat the diaphragms as rigid. There are other times when a rigid diaphragm approach would not be appropriate, and you'd want to model the diaphragms as semi-rigid. So we're going to spend some time in our webinar today exploring which of those two options is most suitable for a number of general types of conditions. So we're going to just start with what is a diaphragm constraint. And I think people using the software understand the difference between restrained joints and constrained joints. So we're really talking about constrained joints. And if you think about the typical body constraint, you can think of two joints that are connected together rigidly, and those two joints in any part of a model are going to translate and rotate as if they're locked together. Well, a diaphragm constraint is a little different. It means that all of the joints that you assign to a rigid diaphragm constraint will translate and rotate as if they are all connected together in the XY plane. But in the vertical direction, the joints can have differential displacements. So it means we're really talking about the membrane behavior of a floor. So if we assign a rigid diaphragm to a floor slab or metal deck and concrete, then the program will treat all the joints on that diaphragm as if they are locked together and inhibit any differential movement within that membrane. So effectively, all the constrained joints are connected like they are linked together rigidly, but they don't inhibit out-of-plane deformations. So you could say, well, this is a pretty good idea. I should use that quite often, and it may be very suitable to use it very often. And there are some distinct advantages. You know, one of the big advantages is that it reduces the eigenvalue problem. So the program, it's more efficient. It'll typically run faster. It's numerically more stable. So there are a lot of advantages, especially numerically, to use rigid diaphragms. But there are some disadvantages. And let's explore some of the advantages and disadvantages. So I'm going to just walk through a number of different models here. And but before I do that, let me open up actually one model, which I think demonstrates the difference between rigid body behavior and a semi-rigid behavior. So this is a floor plan, happens to be a 4-story building. It has a large number of bays within the building that are absent any framing elements. And if I were to just look at this is a particular mode shape and look at the deformation of this floor and animate, maybe I'll look in this floor plan and animate the displacement, what you see is that the floor is behaving as though it's a rigid body. There's not a lot of differential displacement in any one, in the XY direction, not a lot of differential displacement between any pairs of joints. But if I look at another mode shape here, then clearly you can see that for this particular mode shape, the floor is behaving as a semi-rigid diaphragm. The difference is the semi-rigid diaphragm approach is going to take into account the membrane stiffness, and it's going to use the material properties and thicknesses of the sections as you've assigned them to your model to account for the stiffness. And obviously in this kind of a building, it would be very important not to have a rigid body diaphragm, because that would really change the mode shapes. It would change the dynamic behavior of the structure. So in this case, it would probably be very inappropriate to consider a rigid body diaphragm for this type of a model. So that's what we need to explore and understand, is when is it a good time to apply a rigid body diaphragm, and what are some of the pitfalls, and when it's more important to define these as semi-rigid. So let's just have a look at, I'm just going to stop that. Let's just have a look at some different types of structures with some unique types of issues. So here's one. This is like a large, one of these box retail stores, or could be a large warehouse. And I know you have all seen these types of structures. They typically have very tall fluted decks. And the reason the ribs are quite tall is because they have to channel a lot of water a long distance, and you form a pretty deep trough with water. So these types of decks don't resist a lot of shear. And it's necessary for engineers to come up with a secondary bracing system to handle the diaphragm, transfer of diaphragm forces. So here in this particular model, you can see around the perimeter, there's some cross bracing. There are also some cross bracing which ties across the building in a couple different directions. So if I had assigned a rigid body diaphragm to this structure, there's no way that I get any differential displacement between the joints. There's no strain on the shells or the frame members, and so I'm not going to be able to get any load into these bracing members. So that would be an inappropriate application of a rigid diaphragm in this case. And then what about transfer slabs? You know, if we have a rigid body diaphragm and we're bringing forces down from a tall building, let's say, and at the base of the building, we're going to transfer some of the loads from discontinuous shear walls. And of course, it's something that makes all structural engineers cringe if they have these kinds of discontinuous shear walls. But you have to be very careful to make sure that even if the walls were continuous down through to the bottom of the basement, you may have some additional walls that are going to start to pick up the load. And if you were to assign a rigid body diaphragm at one of these heavy transfer slabs, then you're not going to be able to see what kinds of diaphragm shear you have in those slabs. And it would probably behoove you to model these as semi-rigid, and that way you could track how much shear you have in these diaphragms. And I'm going to demonstrate in a minute just exactly this. Some of the features that you have when you're using a semi-rigid diaphragm, and which features you lose when you use a rigid diaphragm. There are times, though, a rigid diaphragm, for instance, if there are some small appendages on the structure and you're really not concerned about these unique mode shapes associated with these small appendages, it may be to your advantage to consider a floor diaphragm as a rigid diaphragm. And it just reduces, as I mentioned before, the size of that eigenvalue problem to be solved, and that can lead to a more efficient design, a more efficient runtime. So there are a lot of examples, and I think you see this in a lot of buildings where there is a pretty significant transition in loads from interior walls to exterior walls, and would encourage you to use semi-rigid diaphragms in these cases. Here's an example of the advantages of reducing the size of the model. Now, we have seen models come into our office which are huge, and it may be that an engineer is trying to conduct a nonlinear response history analysis of the structure. And if you're getting a lot of hinging, and the program is reformulating the stiffness matrix over and over and over, then it just makes sense to try to reduce the total degrees of freedom in the model. And it might be appropriate in many cases to use a rigid body diaphragm when it's applicable, when it's safe to do so. And of course, they're also just, good engineering judgment in terms of getting rid of all of the elements that aren't really going to contribute to the response of the structure, just so that you can reduce the size of the model. There are times when you can, for instance, on this building, there is the need perhaps to define the diaphragms as semi-rigid, because there can be quite a bit of distortion between two different wings. If you have an L-shaped building and you want to find out what's going on at these reentrant corners, then of course it would make sense to model these as semi-rigid diaphragms. But I'm going to look at another building here in particular. It's a little bit unique, and for those of you who aren't that familiar with the ETABS program, the ETABS program will allow you to model towers independent of one another. So it could mean that you have one tower that has a number of different floors, and each of those floor elevations are really independent of an adjacent tower, all connected on the same podium. Now, in this case, you would certainly not want to choose both towers and assign a rigid body diaphragm to those two towers, because you would force those two towers to act as if they are locked together, at least the stories of those two towers. Then I'm going to open up this model and look at it in a little greater detail here for you. So here's the model, and I've run the analysis, and I just want to walk you through a couple of different mode shapes here. So if I activate the first mode, you can see that the displacement of the first tower is really acting quite independent from the second tower. And of course, that's really what you want. You would not want to select all of these elements and assign them to the same diaphragm. And if you just were to look at a couple different mode shapes, you'll see that these are all acting independent of one another. And if you were looking at one particular floor, but all the floors would give us this type of behavior. So they're quite independent of one another. All right. So I'm going to open up another model here and just explore a little bit more about what it means when you have a rigid versus a semi-rigid diaphragm, and how do you assign these things. It's a very simple operation to assign these diaphragms. But let me show you the behavior of the diaphragm when it's considered semi-rigid. And how do I know what's happening here? If I look at a plan view of the structure and I point to any floor element on the structure, and I can see that I've assigned a diaphragm D2, and it's been defined as semi-rigid. And I have the option when I come in here to define a number of different diaphragms. Now, it's okay to use on a multi-story building the same diaphragm type at each floor, because the floors are going to act independent of one another. It's also possible that you could assign different diaphragms to different floors. Some of those diaphragms could be rigid, some could be semi-rigid. So that's also a possibility. But in this case, I've defined two diaphragms, one rigid, one semi-rigid, and if I say modify show, then I'm pointing to either a rigid response or semi-rigid response. And you can make that choice. And as I said, if it's semi-rigid, then it's going to account for the stiffness of that particular shell element or deck element, whatever it is that you have in your building. So I've already run the analysis, and what I want to see are the diaphragm shears. So I can come up and I can look to see what the shell forces are, and I can choose, in this case, it's a quake in the Y direction, and I'm going to look at the F1-2 forces, which are the shear forces in the diaphragm shells. And when I do that, I can see that I have, as I would expect, I have a higher concentration of diaphragm shears where I have bracing elements. And it's pretty easy for your eye to trace where these bracing elements are in each of the, along each of the grid lines. So if I want, I could come in and draw a section cut in here, and I could see how much force I'm transmitting along the shells on this side of the structure. And it's actually a nice section cut because I can see how the shear force varies along the length of that diaphragm, and I could record how much force is getting transferred through the diaphragm. Now, none of this would be available to me if the diaphragms were considered rigid. And I do think, obviously, as structural engineers, you like to understand the load path in a building. And here is a very easy check. I could decide and inspect what's happening here with this diaphragm and say, okay, there's 217 kips that's being transferred through the diaphragm on this grid line M. This is the grid line M here. Here are the bracing elements. How much of that load is coming into the bracing elements? I could also, if I activate this window, I could point to member forces and maybe show the axial forces in these members for, again, quake Y. And then I might come over here and draw another section cut. And I would draw this through here. And I see that there's about 250 kips of force that's being transferred through that brace line. And those 250 kips don't quite match the 217 kips coming from the diaphragm. Well, what's the difference? The difference is the seismic forces that were applied directly along this grid line M. And if I wanted to see what those are, I could come in here and say, display load assignments, joint load assignments for the quake in the Y direction. And if I apply that, I can see all of these forces. And if I were to add up these forces, they add up to about 33 kips, plus the 217 kips coming from the diaphragm equals the 250 kips that's being transferred through the bracing and some load by the columns. So because I've modeled the diaphragm as semi-rigid, I'm able to make these types of determinations about how much shear I have in the diaphragm. And it's just a very handy and useful tool. But if I unlock the model, actually before I unlock the model, I just want to point out a couple of other things. I'm just going to look at in this plan view, the undeformed shape of the structure. Now, I use this as kind of a training model. The deck over here is defined as a shell. On the left-hand side here, it's defined as a deck. But they're both assigned a semi-rigid diaphragm property. But how are the loads assigned for seismic when you have a semi-rigid diaphragm? We know that if you have a rigid diaphragm, the program knows the center of the diaphragm and the center of mass, and it can apply the total force on one point because the diaphragm is rigid. But if it's semi-rigid, you want to distribute the loads, and it's very convenient to do it with seismic forces because we know what the mass is of all the joints. And if we simply come in here and say display, show load assignments, joint load assignments for the quake in the Y direction, you can see that you have a very nice distribution of the seismic forces throughout the building. And that's the way the building is going to see these forces. But what about wind? Wind is a little different. Again, if it's a rigid body diaphragm, the program is going to lump a single force on a single joint. Well, it's actually three forces, two translations and a rotation for wind. But when you have a semi-rigid diaphragm, And let's say the diaphragm is just a metal deck with no concrete fill, so it's quite flexible. We don't want to apply it to a single joint because you could get some local deformation and high stresses at that one joint. So we arbitrarily find 10 points and apply those loads to the structure to help distribute the loads out. Now, it's not necessarily perfect. It's certainly not as distributed as the seismic loads, but we think it's a reasonable approach. So if I look at the wind, this is an ASCE wind case, and apply that, this is wind in the X direction, you'll notice that there are 10 points in here that are being assigned that wind load. And likewise, if I looked at the Y direction, you'll see that the program again finds 10 different joints, and it calculates the force on each of these joints to respect the centroid of the applied load. So there is some effort involved for that to happen. But now let's look at a rigid body diaphragm. So if I wanted to change the diaphragm property in my structure, first you have to unlock the model. And then I'm just going to come over here and say select all. So I have all of the shells selected. I have all of the joints selected. And then you can come up here and say, I want to assign a joint diaphragm, or do I want to assign a shell diaphragm? There is a difference. And in some cases, you may have a mezzanine that has some columns extending, through an open space. So the only option you have is to select the joints and apply either some disconnect to the diaphragm or a different diaphragm property. But if you have a choice to select either joints or shells, the recommendation is that you apply the diaphragm constraint to the shells, because if you have large shells, it's possible that the internally meshed shell joints will not get constrained if you just assign the diaphragm constraint to the joints. So typically you're going to apply the diaphragm constraints to the shells. And if we do that, you would select diaphragm, and I could now select rigid, and I could apply that. And then if I run the analysis again, this will run quickly. And then just to demonstrate, now if I try to come in and look at the diaphragm shears, as I did before, so I'm looking at the quake, same earthquake, same shear force, and apply that. Better point to this window and apply that. Then you'll notice that the program is reporting diaphragm shears of 0. And it's because the diaphragm is locked up with a diaphragm constraint. There's no deformation. There's no deformation. There's no strain. If there's no strain, there's no stress. So, bear in mind that you lose some of the features of the program when you consider these diaphragms to be rigid. But again, there may be more advantages in the overall response of your model to consider the diaphragm as rigid. It's one of those check boxes that you have to examine on each and every model and ask yourself, what features do I need in this model? And the choice of diaphragm modeling will be an important choice for you. So let's explore a couple of other conditions here. So we talked about having a mezzanine. So here is a case where I just created some columns that are separate from another part of the building, and it may be that if you had assigned a diaphragm constraint over the whole model, and you want all of these elements to respond as a rigid diaphragm, you probably don't want these elements to be, there is no connection, so you probably don't want these elements as part of the same diaphragm. So you could select, in this case, the joints. There are no shells to assign a diaphragm to, So here's a case where you would come up and say assign, but in this case you would point to joints, diaphragms, and you might, in this case, choose disconnect. You want to disconnect these joints from the other diaphragm assigned on this floor, and you would apply that. Otherwise, as this, if they're connected as one diaphragm, all displacements and rotations of this L-shaped part of the building would be imposed on these columns over here, and that's likely not what you want in your model. All right, a couple other examples. Just getting back to the way the program assigns loads when you have rigid and semi-rigid diaphragms. So here's a very irregular structure. I mean, just consider if Picasso was an architect, you might wind up with something like this. The point I'm trying to make here is that the diaphragm, there are only a fixed number of points that the program can find to assign wind loads. So if I come up and display what the wind loads are, point to these joints, I created a wind load case. These are user assigned wind loads. And if I say show the wind load, well, if they're user assigned wind loads, the program wants to assign these things to a single point, but there is no joint nearby. And so the program is going to look for the closest joint to assign these loads. And you know, I have some internal meshing on this slab, but it's going to look for an externally meshed joint to assign these loads. You have to be a little cautious about that. Just recently, a question came in. Engineer had a rectangle, and he had assigned the user-defined wind loads on a semi-rigid diaphragm, and was wondering why he was finding these a huge amount of torsion. Well, the closest joint happened to be a significant distance away from the center of the diaphragm, and it's the next closest joint the program could find, and it was inducing quite a large eccentricity on the applied load. So be a little bit cautious. One way to avoid this is just to simply come in and draw a joint, and then let the program go ahead and assign. The program would find that joint, and then it would assign these loads to that joint. Likewise, there aren't a lot of defined joints on here because this is an internally meshed diaphragm. And if I were to come in here and display the load assignments, joint load assignments for the wind load, you can see that the program, it struggles a bit to find 10 joints to assign. It will find these easily, but it may not be the location that's best suited for applying these loads. Yes, it's distributing the loads out. These are wind loads, but you can have a little better control over how the wind loads get assigned by introducing some other joint elements in here. I apologize. So let's have a look at some other models here. What about an outrigger truss? So it's also possible that with the outrigger truss, you could, and this has happened more than once, where an engineer will send us a model and they're complaining that they're not getting any force out of the top and bottom chords. Well, as soon as we hear the question, our first question back to the engineer is, are you using rigid diaphragms? And if they are, of course, that's why the joints along the top and bottom chords of the truss would be restrained by the rigid diaphragm. They would not; those joints would not be able to move relative to one another, and therefore they will not be able to load the top and bottom chords if you have a rigid diaphragm. Now, it may also not be suitable just to say, all right, I'll use a semi-rigid diaphragm. And if you have an 8-inch concrete slab, you would also inhibit load going into your top and bottom chords of your truss. So there are times where engineers have to pay a little more attention to the load path and make sure that if you want 100% of the load to go into these elements, you need to make sure that there aren't elements that are going to share or inhibit the load path to those elements. All right, I want to point to another feature that's within the program. It's a little bit hidden, but I think you'll find that this is a very powerful tool, and it's one that I think engineers can make good use of. So if you are tasked with designing the chords and collectors in a building, and you've decided, well, I don't want to use a rigid diaphragm because I won't be able to get forces out of the program on the floors if it's rigid. So I'll assign a semi-rigid diaphragm. The problem is the semi-rigid diaphragm, the load to the chords is going to be shared by the membrane, the shell elements that make up the membrane. And that means that if you want to be conservative in the design and treat all of the forces to be carried by the chords, then you need to do something else. And this is a nice tool to help you come up with these chord and collector designs. So if you have run an analysis, and in this case, this is a rigid diaphragm. So even with a rigid diaphragm, I can get some good information out of here. So I'm looking in this case at the third story. On the third story, the program has applied for a seismic load, a force here of 33.26 kips. Well, how is the force resisted? The program will show how much force is going to each of the lines of resistance. So if you had shear walls or braces, the program will sum the forces along those lines and report those at each of these joints. And so the way that you activate this form is you come in here under display, and then there is force stress diaphragms, and down here you'll see this diaphragm force button. So in our discussion today, we've only visited a few forms because there really isn't much difficulty in assigning a diaphragm. So and here's one other button for you to remember, and this is how to get diaphragm forces out of your analysis. So if you can remember pathing from the display to the force stresses diaphragms, and then to this diaphragm force icon and click on it, then you have some choices about how you want to view the resultant force. Do you want to show the applied loads? Do you want to show the resistive forces? And do you want to activate the values so that you can read the values off the screen? And then there's a scale factor, and you can apply that. So what would we see if we had used a semi-rigid diaphragm? So I'll unlock the model, and another way that I can select all these elements is just to say all stories or similar stories, and then sweep across each of the floors so that I'm grabbing all of the shells, and then say assign shell diaphragms. And I only have one diaphragm in this model, so I'll just change its property, modify show the diaphragm. It was rigid. Now I'm going to make it semi-rigid. I'm going to apply that, and I'm going to rerun the analysis. And now I'm going to go back to that same form. So it's display, forces, stresses, diaphragms, diaphragm forces, and I'll show the applied loads, and I'll say apply. Here is show applied loads. So it's a little different now because If it's a semi-rigid diaphragm, as we discussed before, the program is going to assign forces to each of the masses. And so I have more points of applied load, but I can also see how the forces are being resisted along each of the lines. So these are some, I think, helpful tools that will enhance your modeling within the ETABS program. And that's, of course, our goal by conducting these webinars. So let me just peek down here to make sure that I have mentioned each of the models that I wanted to. And I believe I have. So at this point, I will entertain some questions if there are any questions out there. Okay, one of the questions here is, how do I identify a diaphragm as rigid or semi-rigid? If, you know, it's very possible one of your colleagues asks you to do a peer review of a model and you have a model in front of you. One way to find out, of course, is you can point to the model and you can, if we're looking at the undeformed model, point to a particular shell and it might say diaphragm D1. Well, sometimes in the naming, it's nice to define what D1 means by assigning as part of the name rigid or semi-rigid. But if you don't know, then you could come in under the define menu and point to diaphragms. And then you can say modify show and see whether it's defined as semi-rigid or rigid. But that's the best way. All right, well, I don't know that we see a lot of questions here, which is good. It means that that this all maybe sunk in. Here's another one though. If the model is small enough or the running time is not too much, would it be valid to assign semi-rigid diaphragms? And you know, the answer is absolutely. But you do have to take into account you know, that yeah, semi-rigid diaphragms are probably going to give you the best solution. And if you're not hindered by a long run time, it's probably a better choice. So certainly, there were times years ago that engineers could choose to model just the lateral system such that they only included shear panels or concrete shear walls or braces, and eliminated a lot of the other structure. The disadvantage of that, though, is that you have to manually assign the gravity loads as part of your column. And if you're conducting a P delta analysis, you really need the entire mass and weight of the structure. So in order to account for that, you would have to model a leaning column, let's say, and it's just more burdensome for you to do that. So oftentimes it is just simpler to model the whole building. But that being said, engineers, I think, need to use some judgment. Now, there are cases, let's say, where you have girders or beams that are spanning in one direction, maybe floor joists marching along at 4 feet on center, and they span 40 feet. Well, do you want to model each of the joists, or for your seismic model, you might choose to eliminate each of the individual elements and just come up with an equivalent deck? The load path is still the same. You're still accounting for the proper gravity load path to the columns, but you've eliminated a lot of detail. Now, if the model is small enough, there's no worries. But if it's a large model and you're running a nonlinear analysis and you're reformulating that stiffness matrix often, then it might behoove you to cut down on the size of the model. In general, these models run very fast. It's not necessary to do that, but we do from time to time see some very large models, and the only way that you can really work on the model is to reduce the degrees of freedom of the model, which means trying to use techniques like that. All right. So I don't know that I see. Oh, here's a question about ramps. Yeah, so what about ramps? These diaphragm constraints are really intended to be applied on a story by story level. And oftentimes in a parking garage, or there are other cases where you have a bridge connecting floors at different elevations. You can model sloping shell elements, and you probably want to avoid assigning a rigid diaphragm to these sloping elements. It's really not intended to work that way in ETABS. But if you draw the sloping shells in there, the program will account for the stiffness of those shells, and you will get restraint or loads carrying from one floor to the other. One other thing to remember about constraints, if you go back to our very first part of our discussion today, considering two joints, if you have two joints which are constrained and you have a lot of force that's potentially being generated between those two joints, if the joints are constrained, there's no way to find out how much force is being transmitted between those two joints. So it may be necessary not to use a constraint, but to put in a very rigid element. And then that way the program will report the forces in those elements so that you can determine how much force is being carried between the constrained joints. But that's really the only way. That's why, assigning constraints in a model, you just want to understand what type of behavior you're introducing to the model, and understand what the advantages and disadvantages are. That's really the whole purpose for having this webinar today, is just to explore some of these advantages and some of the disadvantages. And we're just providing a tool for you guys. This is the engineering judgment that comes from your side, and we just provide the tools for you to handle these things. So I don't see any other questions here for the time being, but if I do find some that I might have missed, we'll definitely respond to all the questions, as anybody that's attended the webinar today will send those back to you. So I will mention we will have an upcoming webinar. We have a new program out. It's just been out for a short while. It's a detailing program, and it's a very interesting tool. The program does generate reinforcing steel for an entire building, and it produces a whole series of drawings, and it's a very nice feature. It allows engineers to view rebar cages, look at how congested reinforcing steel might be in a particular building, and you can, in terms of inspecting a job site, you're out at a job site, you want to see how much you're inspecting the reinforcing steel, and you see something that doesn't quite look right, then you could bring up a tool like this and actually see what was intended to be at this location and compare that with what you're actually seeing when you visit the job site. So we'll go through in greater detail what this feature is all about in an upcoming webinar. So you might want to keep your eyes open for that. But with that, we'll conclude our webinar for today. And I just want to say thank you very much for participating. And we look forward to talking to you again in the future. Thank you very much.